Right. So let me share the screen with people here. Okay, then we can see it. So the first thing we're gonna do is some properties of equality. But before we go over to this one, I'm actually gonna show you something about equality. So when we're talking about equality, we talk about the balancing in a lot of things, like scales. You need to get the balance. If it's balancing, then it's equal. So both sides, you have the same weight, right? So we use some balancing on scales like this. So this is for more advanced math, I would say. But you can use this for elementary level too. But here, I don't know if you can see this all right. I have 3 times in the parentheses. I used to random number 2 plus 4 squared. Without calculating what that is, I mean, it already shows what it is. We want to make it equal to something, so a different equation. I think it's a fun activity you can do. If I start with like 6, 6, what should I do? Plus, minus, multiplication, division, parentheses, square, whatever you like to. Tell me what you want to do to make it equal to 54. What do you want to do? The same. Any operation you want to do? Let's just play around.
Addition.
Addition of, what do you want to add?
I can't really see, so I don't know. I just was trying to get us started.
Yeah. Thank you. How can I make it bigger? How about now? Is it a little bit better? This is the things that I can go. How about that? 6 plus what? What should I do? It doesn't have to be certain. I mean, it has to be the right answer right after adding something. You're gonna keep doing something operation, okay? So what? Tell me. What, Josie? 28?
40. I mean, you can do 28 if you want.
28. Okay, let's do that. And it's not still balancing, right? That means it's not equal. Which one's greater? Left hand side is greater, right? So we need to do something more. What should I do? What do you want to do? You want to add, or subtract, multiply, or divide?
Plus 10.
Plus 10. So we are adding 10 more, and let's see what happens. It's still not equal, right? So we are getting closer though, right? So what do you want to do now? What are you going to do? What if I subtract something? Is it a good idea or not?
No,
No, why not?
you're not there yet.
Then what happens if I subtract something?
It's even more unequal.
Yeah, because the number goes smaller, right? This number is already smaller than 54, but it goes smaller than 44. So no, that's not a good idea. How about division?
No,
No or not?
it's still making the number smaller.
Exactly, right? So we need to do either addition or multiplication. So what should I do? Addition or multiplication? Addition? Addition, when you're doing addition, you can just add some numbers. When you are multiplying, you have to be also careful because we so far have additions there. If I just put multiplication there, what happens? It multiplies only the 10 because of number of order of operation. We do multiplication before we do addition. So if I put like times 2 there, what happens? 10 times 2 is operated first, that's calculated first, then you add 28 to it and 6 to it. Oh, I was lucky. Yeah, I didn't even expect it. But yeah, luckily we found it, right? So you can also extend the notion of equation here, but also you can show the order of operation there and work on that too. So using only one fun game that you can do with your students, you can always extend the mathematical context there. Okay, always think about it. All right. So that's about the equality. Some of the properties are coming up. So these are the first three properties that we're going to talk about. Looks very simple, but sometimes it confuses some of the students. Let's take a look. Reflexive. It's like reflection, right? So A is A. If you look at yourself in the mirror, you look at yourself, right? So A is A. We use this reflexive property when we prove some theorems in geometry, right? So these are really good properties that you can use for proving something. Symmetric is similar to reflexive. The difference is left-hand side and right-hand side of equations are not equal. But when you're flipping them around, it's still equal. For example, let's say I solved this equation and got 2 is equal to x. Then I can flip them over, saying x is equal to 2. Are you following? So if I went down to 2 equals x, that's same as x equals 2. That is symmetric. Okay? So it's symmetry. Transitive property. If A is equal to B and B is equal to C, then A is equal to C. So what I mean here is, if Tana said she is, what are you? 21. Is there anybody who's 21? Okay, and George says she's 21 too. Okay, so we know that Tana's age and George's age are equal, and we know that Anna and George are equal ages too. So we know that these two are equal ages and those two are equal ages. What can we conclude? We can say Tana and Anna are equal ages too, right? So if these two are equal and the other two are equal, the first and last one can be equal. That's transitivity. Okay. So if I use the balance equation for that, A equals A, what property is that? Reflexive. This one. A and B are equal and B and C are equal. Then we can conclude that A and C are equal. Transitivity. Yeah, transitive property. How about this one? A equals B is same as B equals A. Symmetric. Okay? Right, and here are some more properties that we talked about earlier. Okay, so if A and B are equal, do you see how they are equal? Even if their shapes are different, their weights are equal. I'm adding C to the left-hand side of the balance beam, and I exactly add the same amount on the other side too, and it's still balancing. What did I do? I added the same number on the both sides of the equation, and it's still equal. What kind of property do you think it is? What did I just do? I added something, right? It is additive property. How about this one? What happens? I originally had A on the left-hand side and B on the right-hand side. So even if they are in different shapes, they are actually equal weight. So we can say they are equal. What I had here is now, how many A's do I have? 1, 2, 3, 4, 5 A's. So I multiplied A by 5. And here, what happened to B? I also multiplied that by 5. So if I multiply left-hand side 5 and right-hand side 5, they are still equal. So what kind of property do you think this could be? I just did multiplication, right? So it's going to be multiplicative property of equality. Okay? So here are some of the property about addition and multiplication property. Do you think this will be applied for subtraction? Left-hand side. Let's think about subtraction. What does subtracting mean? What's the definition take away, we did a take away model. So definition wise, it's same as you are adding a negative number. Okay, we didn't do the subtraction yet. The definition of subtraction is you are adding negative number to it. So we're gonna do that later when we're in integer. So when we are doing subtraction, it's the same thing as addition. So if we take away certain amount from both sides, still equal, right? So we can go backwards. So let's say originally we have a plus c equals b plus c. If I take away c from the left-hand side of the handle, I mean the balance bin, and take away c min from the right-hand side too, they're still equal, right? Then division, it works the same way. If I divide this by 5 and that by 5, I get a plus c, still equal, right? So it works for any of the addition, subtraction, multiplication, or division. If you are operating the same thing on both sides, left-hand side and right-hand side, it doesn't change unless you multiply by 0, right? Cancellation properties of equality. So we can cancel out things, right? So for any real number a, b, and c, if a plus c is equal to b plus c, then what? I can add negative c to both sides of the equation, and we can cancel out that c's, right? So we get a equals b. That's a cancellation. For multiplication, how can we cancel out things? We can divide both sides with the same number. Dividing by c means multiplying by 1 over c when c is not equal to 0. Why c is not equal to 0? What happens if c is 0? What happens if c is 0? It gets undefined when you're multiplying that by 1 over c. C is 0, then 1 over 0 is undefined. Very good thinking. Also, if you think about this, a times 0 becomes 0, and b times 0 becomes 0. It doesn't tell us anything about a and b. They can be different. A and b can be different. They can be the same, right? So if c is equal to 0, it doesn't tell us anything about the relationship between a and b. Because, as just Henry said, we cannot divide both by c, because it's undefined. We can't. That's why we say c cannot be 0. If c is not equal to 0, we can now divide both sides by c, and we get a and b on each side. Okay? Zero product property. So we know that 0 is very powerful, and that's why maybe we say it's big back there. It's a very important number in our number system. So if we say, if you got a product as 0, what can we say? That means it's either a is 0 or b is 0. When I say or, it can be both too, right? So a can be 0 or b can be 0, or both can be 0, okay? So we use this a lot of times when we were in algebra class in high school. Remember that? Yeah. Okay, so that's the zero product property. Okay, so here is one example from a kid's textbook. Let me ask you to solve this one. Okay. Not only one way, but I want you to think about how you can model it and how you can use, algebraic equations. And what kind of property can you use to solve this problem? I want you to consider all that when you're solving this, okay? Because you're not just solving this problem like a kid, you are a teacher. You need to think about how you can help your students. Okay? So think about all the possible ways, all the possible strategies to solve this problem. George has had some plastic figures. After he bought 7 more figures, he had 25. So we don't know originally how many Georgie had, right? But he bought 7 more figures, and now he has 25. How many plastic figures did Georgie have before he bought more? Okay, I will pause it here, and then everybody to think about how you can show this to your students? Is there any idea? If this is your problem that you're gonna facilitate in your classroom, how would you bring this question to your students? It sounds like a first grade. Well, how do you do that? Mother?
I would draw like 25 squares or like some kind of drawing, and then I would subtract 7 and have them add what it was before.
Okay, so let me do what Morgan has suggested. So you wanna draw some squares, right?
Yeah,
Okay. How many squares?
25.
You're gonna draw 25 squares. 1, 2, 3, 4, 5, 6. I'd like to have 5, 5 because it shows me 10. And I can easily count how many I am drawing. 15, 20, 25.
And then I would have them cross out 7 of
So
them.
what does this mean?
Just total toys.
Yeah, the total toys that he has now, and then what do you do?
Have them cross out 7 of them.
Why?
To show them how many toys he had before he got more.
So the crossed out means they are the new toys that he got more, right? That's more. Or you can just, make two parts saying that these 7s are the ones that he got more, right? That's another way to use that. And we can count how many are left for the previous one. That's a really good idea. So what we did here is partition or takeaway model. But using the context, I think it's better to say just partition, right? The previous, how many he had, and the new group, another group for the new models that he got. Okay, so that's really good. And what we did is we simplified the model. Simplifying the model. Because we didn't actually draw figures. You can draw the figures if you're really good at drawing figures. We didn't do that. Instead, we represented each of the square as the figure, right? So we simplified the model. That's one way that we can do. I like that so much. And another thing that you can do, for the younger students and they really like the figures, and you have some some figures at home, you can actually bring the figures and show them so they can play with them. I think that's another good idea, right? If it's not available like us, then we can just simplify the model like this, right? That's one way. Anybody else has different idea? Let's continue this idea with some numbers then. If I use a number, what can I do? Even if you show this one to your students, you can play with the numbers too, right? So what can you do? You can extend this model to algebraic thinking. Can I have Madison tea? You have any idea?
To make an equation,
You want to write an equation like what?
we do 25 minus 7,
25 minus 7? You want to find that?
which would equal x, which would be.
Why minus 7? Because I don't see anything minus there.
Because you're trying to find out what he originally had.
So originally have, do we know that or not? We don't, right? So can we put that as some other variable, like x, or we can put a square like blank? We can do that. So originally we can start from, we don't know how many there are, so we can put that as x. We can define that, what is our x? The number of? The number of what? Figures that Georgie had before, right? Georgie had before he bought new or more. And before he bought more. My handwriting is bad, but I know you can do better. So always define what your variable is for your students, okay? So that's what we are figuring out. But by looking at this diagram we did, we can just represent this original ones as x. Then these are partitions, so we can just add the new one. He got more, so we usually use the addition there. Now he has 25. From there, we can show, oh, the relationship here to solve x, we can do 25 minus 7, right? So we can come to this equation, and then we can just add that, right? But when we are doing that, we can also talk about some property that we use. What property did I use? What property did I use? From here to there. Jim? What property did I use here? Committed property? What did I commit? Not really, right? Because commutative property, if you're thinking about that, commutative property means like in addition or multiplication, a plus b is equal to b plus a. So you are commuting the addends or multiplication, so you would commute the factors like that. That's commutative property. I didn't actually write the commutative property because I didn't do x plus 7 is equal to 7 plus x. Right? If I do that, it's going to be commutative property. But not really. But I did something here. What did I do?
Is it additive? Because subtraction is still addition, just the opposite.
There we go, Emily. Thank you so much. So I added -7 on both sides, or subtracted the 7 on both sides. So what I actually did is subtracting 7 on both sides. So I canceled this. So there's a cancellation property, right? So I canceled these, and I had a 25 minus 7 there. Okay? So what is x now? 18? Are we good? Okay. So you know how we can extend the notion from the actual figures to simplify the model to algebraic expression. Okay? All right. Okay. Any questions so far? No? Okay. We can do actual models. This is also simplified models, but this one actually shows the balance thing here, right? So n is represented as what is not known, previous number of figures. And he added 7 more, now he has 25. Now he can take away 7 from both sides and find it out, and it's 18. Okay? So you can subtract the same number from both sides, the equality doesn't change. Okay? That's another property. And I like this bar model so much. So I'm going to introduce you this bar model too. Using the exactly same question, we can say that we use the x, so let's use x as unknown numbers, okay? So the same definition, I'm not going to write it, but we can use the bar model. What we know right now is we added 7 more to the previous numbers, and now how many do we have? Total is 25. This kind of a bar model is heavily used in Singapore math. I think I have showed you Singapore math last year, remember? If you took any math 285 from me. Do you remember the bar model that we did? Yeah, so this is very, very useful to solve algebraic, problems, like problem solving strategy. This is one of the best strategies gestures you can use because bar is very flexible. It's not like number line. Number line you have certain numbers in the number tag with same space. So like 96, you need to make 96 of them, and it's a kind of trickier. The bar model like this, you are very flexible. You can just show this bar here is unknown number, for x plus 7 is 25. To solve for x, you can take away 7. You can just x that out, right? In order to do that, you can just subtract 7 to find x. So that's another good way to solve this problem. And I believe the last one here is the equation that we did. Yeah, so we can do that. Okay, here's another example that we need us to think about. Cabrini had some markers. After he bought 12 more markers, she had 16. How many markers did Cabrini have at the start? And n represents the number of markers Cabrini had at the start. So tell me about this. How you would like to teach this to your students? Let's think about all the models that we can think about. Okay, Alyssa Leach, what's your idea?
For this problem. Okay.
What strategy do you want to use? Help your students.
So then you could put the 16 at the 16 equals 12 plus n, just for the number of markers. And you could take negative 12 and subtract.
Okay, do you want to start from 16
Yeah,
equals, or do you want to put n plus 12 first?
you could, I think either way, you could put 12 plus n or n plus 12 and then equals 16.
So we can do either way?
Yeah.
What property is this? If 12 plus n is equal to 16, then 16 equals 12 plus n. Yeah, that's right. Great job, Anita. What property is this?
Is that the reflective?
It's not actually
Or would it be
symmetric.
symmetric? Oh.
Reflective is like oh, hold on. No. X is equal to so this is symmetric. The reflexive is this. Reflexive is you are yourself. Like x is equal to x, a is equal to this is symmetric. Okay, that's reflexive. This is symmetric. Very good. Okay, and then what? Either way, if you use this one, what would you do next?
Subtract 12.
Oh, you would subtract 12 from both sides.
Okay.
And then
For
n
your advanced
equals
students,
4.
There we go. Thank you. So for your advanced students, you can do this one. How about a little bit lower level? They need to have some diagram. What would you do? Shall we use bar model? Let's think about bar model. And I want you to think also about number line too. So let's use the bar model. If I use bar model, how can I do that? How about you do this on your paper first? I'll give you like 10 seconds. And then I want you to think about number line too. Okay, Madison, can you tell me what I need to do here? Sense from?
Does it just fill it up to 12 or whatever? Like make 16 spaces or whatever, but only fill up 12 of them?
For bar model, you don't have to make equal parts there for 16, right? You can be more flexible, like, you know, this whole thing is what? 16, and we have two partitions, two addends. What do we have? 12 and n. So I don't know how I can break it. It can be flexible, right? I can put 12 and n there. This is representing 12 plus n is equal to 16. And to solve for n, what can I do? I can take away 12. Oh, wait. So from 16, I can take away 12 and get 4. So, what did I call? Elisa, how can I do with this number line? We didn't do number line yet, but let's think about it.
Could you like put the start at 12 with like a dot and then have it jump to 16?
So what do we jump first? From 0 to what first? To represent this situation. First,
0 to 12. To 12.
12, yeah. So you jump to 12, that's what it's represented here. Then we added some number. We don't know what that is. And where do we land? Total we have
16.
here. Does that represent? Yeah, that doesn't actually represent the situation here. So let me redo this part. So to represent exact context, we actually start from 0 because it says Kat Rainey had some markers. We don't know how many she had, right? So we start from actually jumping to n. We don't know what that n is. That's what she had at the beginning. We don't know how many she had. So starting from n, I would go that way instead of this. And same for this one. I will go from n, because that's the first number, then I will add 12. Same for this one. I will start from n and add 12 because I want to represent the situation we have now. Okay? Even if you know property works for using commutative property there, but that doesn't actually represent the situation. So let's try to represent the situation exactly. So Cabrini had some markers and many markers, and then she got 12 more. So we are adding 12 more, and where do we land? Now she has 16. So this actually represents the situation, right? To solve for n, what can we do? We know that is n plus 12 situation. So to find the n, we can do 12 minus 16 minus 12. So n is equal to 4. We can do that, right? All right. Another way to use the number line going backwards, you can go minus 12 to the left, right? And you can see 16 minus 12 then, using my blue, going backwards. If I do minus 12, where do we land? You go 16 and go backwards, and you land on 4. You can find what n is. Okay? That is actually cancellation property because plus 12 minus 12 that's 0, and you can find what it is. Any question? Okay, so we actually showed, equation. We showed number line here, and we did bar model, and we did algebraic expression there. So yeah, there are several ways that you can, use as strategies. It depends on how your students' understanding is. Okay, so let's look at one more. Oh, not one more, but I actually gave you several problems. Now we can mean the actual models, okay? Now we can use this algebra. Solve each of the following equations for x. When you're solving for x, think about what property you are using there. Okay, so I will give you about 1 minute to solve all these 4 problems. 1 minute, 50. show you a calculator. Okay, any volunteer for the first one? It's the easiest one.
Subtract 4 from
Okay, Anna, do you want to subtract 4 from both sides of the equation? What property is that? It's another addition property of equality because you added a negative number, right? Okay, so what you did is you added or subtracted the same number on both sides. Equality doesn't change, right? That's really good. What happens here? Plus 4 minus 4. Cancels out, so we get 0 and x plus 0 is x. So 20 minus 4 is 16. Very good. How about this one? Anybody here? Morgan.
I did subtract x from 3x, and then the x goes away on that side.
Both sides is still the same, right? Same property, okay?
So then that's 2x
You can
equals
cancel this out. Okay, and left hand side,
2x equals square root of 10.
that one.
And then I divided that by 2.
Now, if you multiply 1/2 on both sides or divide by 2, the equality doesn't change. So you can divide both by 2 and get x is equal to square root of 10 over 2. Very good. Any question for that? How about try C? Anybody here? There are several strategies. So what's your strategy? How many of you changed everything to fraction with 1/3? Nobody? And how did you do? Madison, go ahead.
I have no idea on this one.
Jalen? Hannah? How about another Madison? S? No? Julie? Haley? You're figuring it out? What was your strategy?
Well, I started by getting all the like terms together.
You mean x terms together?
Yeah.
Oh, okay. So there are two ways, okay? I will show you both. Okay, first, you can change everything to 1/3. Okay, so 4/3 x is equal to 1/3 x minus 1/3. 33 is the same as how many thirds? Louder. 11, what did you do? You multiply this by 3. Is that actually 11, right? Because 33 over 1 is 33, and you multiply this by 3, then you can multiply this by 3 as well. So it's actually 99. So 99x. Now you can see that everything is in thirds. So you can either keep that as it is, but for me, I don't like the fraction. So I'm going to multiply 3 on both sides of the equation. I can multiply 3 on left-hand side and right-hand side as well, right? So if I do that on the left-hand side, what do I get? Let's copy it down. What do I have? This will be canceled, and I have 4x. the right hand side. I have canceled this out. Yeah, 99x minus 1. So it's, I think it's a little bit simpler. So would you like to take away 4x or 99x? 99x, you can do that, but you get negative number there, right? So for me, it's okay, still good. But for me, I like positive number, so I can take away 4x instead. It's still okay. Let's see what happens then. So I have 0 is equal to what? 95x, and I have negative 2 there, right? So if I add 2 on both sides, I have 2 is equal to 95x. Now I can divide both by 95. What I have here is 2 over 95 on the left hand side. Right hand side, I have x, right? 95 over 95 is 1. Are you following?
Where'd you get the 2?
I added 2 on both sides to get rid of the negative 2. That's a good question.
Yeah, no,
Yeah,
but
but you
it's
get the
negative
negative
1.
just would be 1.
What is it?
You're supposed to just bring
it
down
is,
the
it
negative.
is. Good question, yeah, so it's actually 1, isn't it? I was rushing because Kyla's here. So actually there's 1, right? Then I have 1 over 95, and that's x. And now, I can say because 1 over 95 is equal to x, I can say x is 1 over 95. That's right? What property is that?
So why don't you have to factor the 3 back in?
What is it?
Why don't you have to factor the 3 back in?
I don't factor that out. I multiply the 3, or you can factor out 1/3 out.
So you don't have to put that back in at the end?
You don't, because I still have the same equation. It's still equal. Maybe it's a little bit confusing for you guys, and I was rushing and I feel bad about it, so I'm gonna do C and D again when we return on Friday. Sounds good? And Kyla, is something to make an announcement, I guess?
Hi everyone, I think yesterday you should have gotten your placements for math clinical experience. I have a physical copy of the letter and the schedule information for you. So I have a folder for middle school, intermediate, and primary. If you forgot where you're placed, I do have a list